This video will describe how information-backed discrete repetition replay can be used for incremental learning. Current deep neural networks suffer from catastrophic forgetting. That is, when the model is continuously updated using novel incoming data, the updates can override knowledge acquired from previous tasks. Incremental learning aims to design systems that can keep learning new knowledge while maintaining the performance for the previously learned tasks. Replay is the most competitive and popular strategy. This is usually achieved by saving a subset of old data. Replay-based methods achieve state-of-the-art performance on many benchmark datasets. Although carefully selected exemplars or generated representative exemplars can help improve the performance up to some degree, the larger number of exemplars a model inherits, the better performance it can achieve. Thus, finding a trade-off between the memory limit and the scalability of the model is still an open problem in replay-based incremental learning. We approach this open problem by tapping into a two-step compression approach named information-backed discrete repetition replay, which allows saving all exemplars at a competitive memory cost. The two compression is enabled by a vector quantized variational autoencoder VQVE, as well as a lossless compression method named a bitspec asymmetric numeral systems (BBNS). The first step is lossy compression. We utilize a VQVE to process the input images and save their discrete latent repetitions in a format called codes that can be later used to reconstruct the original inputs. The codes are much smaller than the original inputs, and in this way, the memory cost is reduced. In the second step, we use a BBNS to further compress codes obtained in the previous step losslessly. BBNS tries to encode each code into a number of bits equal to its negative log probability, assigned by a latent variable model. To learn new classes by a classifier, IB-DRR combines latent repetitions of new training samples with those of old samples from codes buffer and reconstruct them back to the RGB image domain at runtime. To get back the lost information caused by the lossy compression, we propose information-backed mechanism IB that utilizes a contrastive learning loss by maximizing the cosine similarity of the latent repetitions produced by a classifier given raw images and their reconstructed views. We compare our methods with the state-of-the-art replay-based methods. The line graph shows the phase-wise accuracy on CIFAR 100 under three different incremental settings. Our model starts with a lower accuracy at the initial training phase due to the fact that the reconstructed images are of low quality as compared to the original images. Despite this fact, our models can maintain the knowledge over older classes when learning new classes. Our methods outperform other baselines by a large margin according to the results in the table. We also report the memory cost. Saving discrete latent repetitions in codes costs less memory while saving 25 times more exemplars as compared to other replay-based methods. We have also extended this workshop paper and evaluated our methods on the second dataset. Our new results on a subset of ImageNet show that our models also surpass the Celiktutan method by a large margin with a competitive memory cost required for saving exemplars. In conclusion, we formalize incremental learning as a repetition compression problem and introduce discrete repetition replay for this task. We introduce an information-backed mechanism to alleviate the information loss and regularize the training of the classifier. Our experimental results show that our models surpass Celiktutan methods with a competitive memory cost across the different datasets. Thanks for your listening. Please refer the paper for more information about the IB-DRR.